Dear students, today we will discuss Theorem 8.3. Let X be a normed space and Y be a Banach space. So this theorem has two parts. First part, let X naught be a dense subspace of X and F naught belongs to BL of X naught Y. Then there is a unique F belongs to BL of XY such that F restricted to X naught equal to F naught. Also norm F equal to norm F naught. Second part, consider Fn belongs to BL of XY such that norm Fn which is less than or equal to alpha for all n and some alpha greater than 0. Let E be a subset of X whose span is dense in X. Assume that sequence Fn of X converges in Y for every X belongs to E. Then there is a unique F belongs to BL of XY such that Fn of X converges to F of X in Y for every X belongs to X. Okay, so first we will consider a part, that is let X naught be a dense subspace of X and F naught belongs to BL of X naught Y. Okay, then we want to show that there is a unique F in BL of XY such that F restricted to X naught equal to F naught and norm F equal to norm F naught. Okay, then proof of for Theorem 8.3a. Let X belongs to X. Okay, then there is a sequence Xn in X naught such that Xn converges to X. Okay, now we have this sequences in X naught. Okay, and also F naught belongs to BL of X naught Y. Okay, then F of Xn is a sequence in Y. Okay, now since norm F naught of Xn minus F naught of Xm which is less than or equal to norm F naught into norm Xn minus Xm. Okay, for all n m equal to 1 2 3 etc. Now since sequence Xn is Cauchy in X naught, why this sequence is Cauchy in X naught? Since we have Xn is a sequence in X naught and Xn converges to X. Okay, we know that every convergent sequence is Cauchy. So this sequence is Cauchy in X naught. Okay, and from this we have, this is Cauchy, then from this we have F naught of Xn is Cauchy in Y. Okay, also given that Y is a Banach space, then this Cauchy sequence converges to some Y in Y. So let F naught of Xn converges to Y in Y. Define F from X to Y by F of X is equal to Y. Okay, that is F of X is equal to limit n tending to infinity F naught of Xn. Okay, now first we will show F is well defined. Okay, let a sequence Xn and sequence Xn dash be two sequences in X naught such that Xn converges to X and Xn dash converges to X. Okay, then norm of F naught of Xn minus F naught of Xn dash which is equal to norm of F naught of Xn minus Xn dash. Okay, so which is less than or equal to norm F naught into norm Xn minus Xn dash. Okay, so which is less than or equal to norm F naught into norm Xn minus X plus norm X minus Xn dash. Okay, we add and subtract X and then split. Okay, then we have this. So which is less than or which is less than norm F naught into epsilon, since Xn converges to X and also Xn dash converges to X. So this is epsilon by 2 plus epsilon by 2 and epsilon. Okay, so we have norm F naught of Xn minus F naught of Xn dash which is less than norm F naught into epsilon. Okay, so this shows that limit n tending to infinity F naught of Xn equal to limit n tending to infinity F naught of Xn dash. Okay, next we will show F is linear. So for this let x1 x2 belongs to X and let Xn dash xn double dash be sequences in x0 such that xn dash converges to x1 and xn double dash converges to x2. Okay, then f of x1 plus x2, which is equal to limit n tending to infinity f naught of xn dash plus xn double dash. Okay, so this is equal to limit n tending to infinity f naught of xn dash plus limit n tending to infinity f naught of xn double dash. Okay, so that is equal to f of x1 plus f of x2. Okay, similarly we can show that f of kx1 equal to k into f of x1. Okay, so this shows that f is linear. Now we will show f belongs to bl of xy. For this, take an x belongs to x, then norm f of x is equal to norm limit n tending to infinity f naught of xn. Okay, so that is equal to limit n tending to infinity norm f naught of xn, since norm is a continuous function, so which is less than or equal to limit n tending to infinity norm f naught into norm xn. Okay, so that is equal to norm f naught into norm of limit n tending to infinity xn. Okay, this is equal to norm f naught into norm x, since limit n tending to infinity xn equal to x. Okay, so that is norm f of x less than or equal to norm f naught into norm x. This is for all x belongs to x. Okay, so this shows that f is continuous, and also norm f less than or equal to norm f naught. This is our equation number 1. Okay, next we will show f restricted to x naught equal to f naught. So let x belongs to x naught be arbitrary. Consider the sequence xn in x naught given by xn equal to x. This is for all n xn equal to x. Okay, then xn converges to x, and hence f of x equal to limit n tending to infinity f naught of xn. Okay, that is equal to limit n tending to infinity xn me equal to x, so limit n tending to infinity f naught of x, that is equal to f naught of x. Okay, that is f of x is equal to f naught of x. This is for all x belongs to x naught. Okay, so this shows that f restricted to x naught equal to f naught. Okay, also norm f greater than or equal to norm f restricted to x naught. Okay, that is norm f greater than or equal to norm f naught. This is our equation number 2. Okay, so from 1 and 2 we have norm f equal to norm f naught. Okay, now the function f defined above is unique. Let g belongs to bl of xy is such that g restricted to x naught equal to f naught, and norm g equal to norm f naught for all x belongs to x. Okay, now f of x is equal to limit n tending to infinity f naught of xn, where xn is belongs to x naught and xn converges to x. So that is equal to limit n tending to infinity g of xn, since g restricted to x naught equal to f naught. Okay, so that is equal to g of limit n tending to infinity xn. Okay, since g belongs to blxy, so this implies g is continuous, so we can write like this. So that is equal to g of x, since xn converges to x, so we have f of x is equal to g of x for all x belongs to x. So we have f equal to g. So this shows that this function is unique. Okay, so this completes the proof of first part. Okay, next be part of theorem 8.3. Let x naught equal to span of the set E. Okay, then x naught is a dense subset in X. Why? Since given that E be a subset of X whose span is dense in X. Okay, so if we take a span of E equal to x naught, then x naught is a dense subset in X. Okay, let x belongs to x naught, then x can be written as the linear combination of x1, x2, etc. xn. Okay, where xj belongs to E for all j. Okay, then fn of x is equal to a1 fn of x1 plus a2 fn of x2 plus etc. am fm of xn. Okay, now since fn of xj converges in y for each j, okay, here xj belongs to E. Okay, so this shows that sequence fn of x converges in y for each x belongs to x naught. Okay, so we take limit n tending to infinity fn of x is equal to f naught of x for all x belongs to x naught. Now we will show f naught is linear. So for this we take x and x dash in x naught. Then f naught of x plus x dash equal to limit n tending to infinity f naught of x plus x dash. Okay, that is equal to limit n tending to infinity fn of x plus limit n tending to infinity fn of x dash, since fn is linear. Okay, so that is equal to f naught of x plus f naught of x dash. Similarly, we can show that f naught of kx is equal to k into f naught of x. Okay, so this shows that f naught is linear. Now we will show f naught is bounded above or continuous. Okay, so for this we take x in x naught, then norm f naught of x, which is equal to limit n tending to infinity fn of x. Okay, so that is equal to limit n tending to infinity norm fn of x. Okay, so which is less than limit n tending to infinity norm fn into norm x, since fn belongs to bl of xy. Okay, so which is less than or equal to limit n tending to infinity alpha into norm x. Okay, since norm fn which is less than or equal to alpha, that is norm f naught of x which is less than or equal to alpha into norm x. Okay, therefore f naught belongs to bl of xy. F naught is defined in x naught. Then by a part, there is a unique f in bl of xy such that f restricted to x naught equal to f naught and norm f equal to norm f naught. Now let x belongs to x and epsilon greater than 0. Since x naught is dense in x, we can find some x naught in capital X naught such that norm x minus x naught less than epsilon. Okay, this is our equation number 3. Now since limit n tending to infinity fn of x equal to f naught of x for all x belongs to x naught. Okay, so we have a limit n tending to infinity fn of x naught equal to f naught of x naught. Okay, then there exists some n naught greater than 0 such that norm fn of x naught minus f naught of x naught which is less than epsilon for all n greater than or equal to n naught. Okay, since f restricted to x naught equal to f naught, so we have norm fn of x naught minus f of x naught which is less than epsilon for all n greater than or equal to n naught. This is our equation number 4. Okay, then norm fn of x minus f of x which is less than or equal to norm fn of x minus fn of x naught plus norm fn of x naught minus f of x naught plus norm f of x naught minus f of x. So which is less than norm fn of x minus x naught. This is actually epsilon, so plus epsilon plus norm f of x naught minus x for all n greater than or equal to n naught. Okay, so which is less than or equal to norm fn into norm x minus x naught plus epsilon plus norm f into norm x minus x naught for all n greater than or equal to n naught. Okay, so then which is less than or equal to alpha into epsilon plus, so here since norm fn less than or equal to alpha. Okay, so this is alpha into epsilon. Also norm x minus x naught is less than epsilon from equation number 1. So plus epsilon plus norm f into epsilon. Okay, so this is equal to alpha plus 1 plus norm f into epsilon. Okay, so that is this fn converges in y to f of x for all x belongs to x. So this completes the proof of theorem 8.3. Okay, thanks.